Good morning. Let us now look at a full wave rectifier, and in a full wave rectifier basically we are going to use either 2 diodes or 4 diodes. Remember, in half wave rectifier we said it is only 1 diode that is basically used, but for this case we are only going to use 1 diode, and for this case we are going to use 2 diodes and 4 diodes depending on which kind of circuit. Remember, before we have said a full wave rectifier is basically divided into 2. We have a center tapped transformer circuit, and we also have a bridge rectifier circuit. So it all depends. For a center tapped transformer, we will only be using 2 diodes, but for a bridge circuit we'll be using 4 diodes. So in this case we shall employ 4 diodes, but for this other case we will use 2 diodes. So I've said for center tapped transformer we use 2 diodes, for bridge rectifier circuit we use 4 diodes. So those are the 2 cases whereby that we need to differentiate between a center tapped transformer and a bridge rectifier circuit. Number 2 point that you need to understand also is that for a full wave it basically means this kind of circuit is going to utilize the 2 cycles. Remember, we said we are converting, a rectifier converts an AC input into a DC output, meaning an AC input has got 2 cycles. It has the positive cycle, it has the negative cycle, like that. So basically this means this is the positive cycle and this is the negative cycle. So if you have such a circuit that is going to utilize both the positive cycle and the negative cycle, we shall call it a full wave. Because like I said before, a full wave begins from this point to this other point. A full wave comprises of 2 waves, the positive cycle and the negative cycle. So that is what we are calling a full wave. So full wave rectification means the 2 cycles are considered, but in cases whereby you only consider either the positive cycle or the negative cycle, then we shall call it a half cycle. So like I've said, in this case we shall consider the 2 cycles, and that is why it's called a full wave rectifier. So we now want to zero down into a center tapped transformer and look into its circuit, how it is drawn, and basically how it operates. So basically we're going to deal with a center tapped and see how it operates. So when you are using a center tapped, we have said it is using 2 diodes. And basically what you draw is the input point, which is an AC, has to pass through a transformer, and like we had discussed before, the function of the transformer is to bring down the voltages to a reasonable level. This is our input, and remember, the input is an AC. It is a sinusoidal wave. Sinusoidal means the wave takes the form of a sine wave. So it moves in such a manner. So basically this is a sine wave. It's called sinusoidal wave because it behaves like a sine wave. The next thing we have said, this kind of circuit is using 2 diodes. It is using 2 diodes. Let me just make it a little bit bigger. It is using 2 diodes. That is our transformer. So the first diode is on the upper side and the second diode is drawn on the lower side. Then we have also said this is a center tapped transformer, meaning the load is connected at the center of the transformer. So whenever you are drawing, you need to connect your load at the center. So the load will be drawn at the center. So I've said the two sides, the upper side and the lower side, is connected to the diodes, and the center is connected to the load. And once you do that, you will now be able to connect the two ends. You have to short circuit the two ends as shown above. So I've said this is the load. We can say this is diode 1. And we can also say this is diode 2. Let us also say this is our point A. Let us say this is our point B. Let us say this is our X, Y, and Z. Those are the three. Then of course we can also perhaps say this is our point C. We want to use these letters in explaining the operation of a center-tapped transformer. These letters are very important as far as the direction of current are concerned. So basically, when we're explaining the operation of a center-tapped transformer, like we have said before, we have in two cycles. You need to describe what happens during each and every cycle. So we shall start from the positive cycle. In a positive cycle, during the positive cycle, you need to tell us the polarities of the output of the secondary side of the transformer. You need to tell us the polarities of point A with respect to point B during the positive cycle. And then after you do that, you also need to mention the status of the two diodes. Are they forward biased or they are reverse biased? So the first thing is you need to tell us the status of these polarities. So we will say during the positive cycle, point A is positive relative to point B. Or we can say in simple terms, point A is positive while point B is negative. The next point should be what will be the status if this point is positive. And remember, this is as good as saying this is P and this is N. It means the positive is connected to P. And this negative, of course, will be connected to N. Such a diode is forward biased. If the diode is forward biased, it means it will allow current to flow. Remember, when we were talking about biasing, a diode is only able to conduct during forward biasing condition, but it will not conduct during reverse bias condition. So basically, I would say diode. So before I write, we can also check. We have said this negative, this positive. It means this P and this is N. So the negative point is connected to P. That one leads us to conclude that this diode is reverse biased, whereas this one is forward biased. So we can say diode 2 is reverse biased, while diode 1 is forward biased. Hence, it conducts current. It conducts current in the direction. It conducts current in the direction given in the direction. So you need to tell us which direction this current is going to flow. Remember, now this current will flow in this direction. It will begin here like that. So that is what will happen during the positive cycle. That will be the direction of current. The current begins from this point A, it moves through the diode, it gets to point X, comes to point Y. Remember, it has an option of moving downwards, because according to Kirchhoff's current law, upon reaching a junction, current can divide. So part of it will move to this side and the other one will move this side. But because this diode is reverse biased, it will not allow current to flow to this point. Meaning, all the current flows towards the load. That is why we are saying the direction of the current will take this direction. It will start from point A, it will move to the diode 1, it will move to point X, move to point Y, move to the load, then finally it will go back to C. So the current begins at point A, goes to the load, to the diode X, Y, to the load, then finally to C. So basically at the end of the day you will come to realize that this point C becomes our ground, or it becomes our negative point, the actual negative point. So we have analyzed what is happening during the positive cycle. The next step is to move to what happens during the negative cycle. We want to see what is happening during the negative cycle. Want to see what happens during the negative cycle? Can talk about negative cycle. So what happens during the negative cycle? So what happens during the negative cycle? We have to begin the same way we started. You need to tell us the polarities of point A and point B during the negative cycle. Number 2, you will tell us the status of the two diodes. So basically the first point will be, remember during the negative cycle, the polarities will interchange. This was a positive, it becomes a negative. This was a negative, it becomes a positive. So the polarities will reverse. So what happens is, if these are negative, these are positive there, then it means this diode is reverse biased. We have said point B will become positive, this diode will be forward biased. I hope you understand that concept because we have gone through it in our previous classes. So the first point here will be point A is negative, while point B is positive. The next point will be the status of the diodes. We have said this is positive, this is negative. If this is positive, this diode is forward biased, this one is reverse biased. So we say diode D1, we can say diode 1 is reverse biased, while diode 2 is forward biased, hence it conducts current in the direction given us, So basically we have said our current will begin here, it will move in this direction like that, like this, and back to point C. So it begins here. And just make it a continuous line, there is no problem. So during the negative cycle, that is what happens. The current begins at point B, goes to this point. Remember this was our Z there. So the current begins at point B, goes to the diode, point Z, point Y, and then it comes back to C. So basically what will happen is this. We will say the current begins at point B, it goes to the diode 2. Then after diode 2, it goes to Z. After Z, it goes to Y. It goes to the load, and finally it goes back to C. So we can talk about the conclusion. What do we conclude about the operation of this circuit? You can see at all times during the positive cycle and during the negative cycle, the current flows from point Y to point C. You can see during the positive cycle, current took this direction. It goes to X, comes to Y, then back to C. During the negative cycle, it moves to Z, Y, then to C. So at all times, in both cases, the current flows from Y to Z, meaning the load experiences a unidirectional current. So we can say in both cycles, the load experiences unidirectional current. Unidirectional current means current flows in the same direction. So in both cycles, the load experiences unidirectional current, i.e., current through the load is from point Y to C in both cases. So that is the conclusion you can make about this circuit. We can just draw the waveforms. You can draw the waveforms. So when we talk about the waveforms, basically what we mean, we are trying to compare the output and the input. So what we were having at the input is a sinusoidal waveform. We have said whatever that is coming in is a sinusoidal waveform, like that. That is the shape of the wave that is coming in. And whenever you are drawing this, remember I've said this is the input, this is the voltage, that is the voltage. You can make some dotted lines to assist you identify the output. So what happens is, we have said during the positive cycle, the load will receive some power. Will receive some power. So we have to maintain the same shape will be maintained such that we have this like that. During the negative cycle, the load also receives some power. So instead of drawing it at the lower level, we also draw it at this point like that. During the second, remember this is the first positive cycle. Can say this is the first positive cycle. This is the first negative. This is the second positive, and this is the second negative. So during the first positive cycle, you draw it up there. During the first negative, you draw it there. During the second positive, you still draw it here. During the second negative, you also draw it up here. So that is how the output will be looking like. If you put a CRO, the cathode ray oscilloscope, to measure or to display the output waveform, this is what you are likely to see. But if you put the CRO at the beginning or at this point A and B, you'll be able to see this kind of wave. But if you put that across the load, this is the kind of waveform that you will be able to see. Finally, if you connect a capacitor across the load, the function of the capacitor is to smoothen the output. is something that is called smoothening. Smoothening means you want to make this kind of output to be as direct as possible, to remove any traces of AC waveform that might have sneaked. Remember, the function of the diode is to ensure that you have done rectification. You have converted the AC signal to a DC signal. But unfortunately, like any other machine, which cannot be 100% efficient, so meaning you cannot be able to completely convert AC to DC using this diode. Some traces of AC will sneak to the output. So for you to remove that, you need to come up with a section that is called the filter. Remember, we have discussed this in the block diagram. So, and a key component that is used in filtering section is using a capacitor. So if you connect a capacitor across the load, at this point, for instance, like that, this output will be smoothened, and this will be the kind of shape that you will experience. You will be able to find this. But because we have connected a capacitor, so what will happen is this: you will be able to identify something of that kind. These ones are drawn in dotted lines. So you will be able to find this. Then at this point it goes a bit straight like that. Then it comes this direction. Then again it goes in such a manner. It goes up. Then this will connect the other side like that. So basically the output will be taking such kind of a shape, almost a straight line. But you can see for this other case, it has to go up, down, come up, go down. But this one, we are trying to achieve something that is almost a straight line. And those are the three waveforms that are normally examined. You need to understand this concept. So with those few remarks, we want to stop there until our next session. Thank you.